Okay, so because we've got done studying exponential functions, I think it's a great time to, just like when we did linear functions and we talked about arithmetic series and sequences, because those are just linear functions, geometric series and sequences are also our exponential functions. So, and what happens is, you remember how we went y equals ab to the x? And the b was the multiplier. So, depending on which you're multiplying, that's what it is. So the same thing here with if you look down here at the explicit definition for a geometric sequence, do you see how it's the same thing except they have the n minus 1 instead of x? That's because here we use the y-intercept to find these equations, and here we usually use the first term. So that's like when x equals 1. We can certainly rewrite these like y equals ab to the x, and that's not wrong. It's just more work. Why do it? So the way you find out the multiplier, because they tell us consecutive terms, or generally tell us consecutive terms, is you take the second term divided by the first term, see if it's what that is. Take the third term divided by the second term, see if it's the same as the first one. Then you know it's got a geometric sequence going on. And then the first term is the a sub 1. If you want to do recursive definition, just like with arithmetic, you start a sub 1 is the first term, you write down whatever that first term is, and then to get the next term, you take the last term and multiply it by the common ratio. And that's just building the sequence. So I've got some examples down here on the next page here. Next page, let me go to the next page. Okay, so this is an assignment. This is an assignment that I also blend, usually when I do them together. So we're only going to look at parts of this. I might have had you do these other ones earlier in the year. I don't remember. So they're telling me these sequences are geometric. So they're telling us they are. So let's see what R is, and we can kind of tell. So I'm going to do 26 or 25, and then I'm going to be quiet. Let you do 26 and come back and check your work, and then maybe we can do one with the alternating signs because they're a little weird. Okay, so I see 6 divided by 2 is 3. I see 18 divided by 6 is also 3. So they're telling me it's a geometric sequence, but even if I didn't know that, I could say, I see, okay, in 54, let's check out. What's 54 divided by 18? Well, I think that's 3 also. So yeah, we get a common ratio of 3. That's R. What's my first term? 2. So they want us to do a recursive rule. Well, let's do this. So a sub 1, not a sub n, Dan. Where's my eraser? Maybe undo what I wrote. A sub 1 equals 2. Then to get a sub n, I have to take a sub n minus 1, the last term, and times it by 3, because that's the common ratio. So that's the recursive formula. So then if they wanted me to do the explicit formula, that's where we take a sub n equals your first term, which is 2, times that common ratio, n minus 1, or x minus 1, whatever you wanted. So there's the explicit formula. They want me to find the 8th term. Well, I could certainly multiply by 3 or 4 more times, but I could also just say, what's a sub 8? That's equal to 2 times 3 to the 7th. Remember, n is 8. I'll write it down this way, but I'm hoping you can just remember it's 3 to the 7th. And that's going to be a big number because 3 to the 7th is pretty huge. So 3 raised to the 7th power is 2187. Here, I'll write that down for those of you that like me to write out more things. 2187. Then I got to multiply that by 2. And so the 8th term is 4374. So I've done the common ratio, the 8th term, recursive rule, and the explicit rule. Why don't you go ahead and try number 26? Stop the video, come back and watch me do it. So I'm assuming you've stopped the video and you're coming back to watch me do this. So let me delete. Actually, can I just delete? That's x. That's what I want to do. There. Whoops. Nope. I don't want to delete. I just want to delete this. Here. Delete. There we go. So I spy with my little I, 6 divided by 3 is 2, 12 divided by 6 is 2. That tells me R is 2. So to get the recursive rule, I'm going to do a sub 1 equals 3, a sub n equals a sub n minus 1 times 2, because that's a common ratio. My explicit rule is a sub n equals 3 times 2 to the n minus 1. And then to find the 8th term, what's 3 times 2 to the 7th? Well, isn't 2 to the 7th 256? Is that one of the ones I had you write down the exponential? No, it's 128. So 128 times 3 is 384. Okay. So that is that. Let's look at number 27. Number 27 is what here? So I see it's alternating signs. So negative 2 divided by 1 is negative 2. Same thing, 4 divided by negative 2 is negative 2. So R is negative 2. So that just means that you're going to alternate signs when we do that, right? So the recursive rule, a sub 1 is 1. A sub n equals the last term times negative 2. The explicit rule is a sub n equals 1 times negative 2 to the n minus 1. And then for the 8th term, it's going to be, let's see, so it's the same thing. It's going to be 2, so it'll be, so it's 1 here. Let me do this. Let me move this up. So to find a sub 8, it's going to be 1 times negative 2 to the 7th power. We just said 2 to the 7th was 128, but because it's an odd number, it's going to be negative 128 times 1, right? It's negative 128. So it's that easy. So if you want, you can do the next one. Why don't you stop the video and come on back? So I'm seeing, let's see, 2 over negative 2 is negative 1, and that's, so R is negative 1, right? We don't have to do too much more for that. So a sub 1 recursive rule, first term, next term equals the last term times negative 1 in this case. And then the explicit formula is going to be a sub n equals, negative 2 times negative 1 to the n minus 1. And for the 8th term, what's a sub 8? Well, that's negative 2 times negative 1 to the 7th power. Well, a negative number to an odd power is negative. Negative 1 times negative 2 is 2. Easy enough. Okay, so for this one, let's see, for number, so we're going to look at number 31, because that's the next geometric one here. They're telling me that a sub 2 equals 3. They're telling me that a sub 8 is 192, and they want me to find the first term, common ratio, and explicit rule. Well, let's see. I know that 3 equals the first term times R, because that this is the second term. I just have to multiply the last term, the first term times R, so I don't know what that is. But then I know that 192 equals a sub 1 times R to the 7th, right? Because it's n minus 1. So can't I do this? Can't I say that it's kind of like doing those exponential equations that we just got done doing. Isn't R equal to 3 divided by a sub 1? So then I can replace that. No. Let me do this. Yes, I could do that, but that's a hard one. No, let me change gears here. I'm sorry. I want to divide by a sub 1. I want to divide by R here. So I'll divide by R, and a sub 1 equals 3 over R. So that'll let me do 192 equals 3 over r times r to the 7th. See how much easier this is? Now, if I have an r to the 7th divided by an r, isn't that r to the 6th? So 192 equals 3 times r to the 6th. 192 divided by 3 is 64. And the 6th root, I know that 2 to the 5th is 32, and 2 to the 6th has to be 64. If you didn't know that, you'd have to do the 6th root of 64. So you would get that r equals 2. And since we know r equals 2, a sub 1 is 3 over 2. And they want, now we're almost done here. They just want us to do a explicit formula. So a sub n equals 3 over 2, that's a sub 1, times 2 raised to the n minus 1. What's wrong with that? We could, I'm not expecting to do this, and I wouldn't do this, but we could, here, can I move this up some more? We could say, isn't this 3 times 2 to the n minus 1 divided by 2 to the 1st? Because that's just all multiplication. And when I'm dividing like bases, I can subtract the exponents. So won't that be 3 times 2 to the n minus 2, because I'm taking away 1 more from that? So that'd be another way to write that, though that's not a nice explicit formula like that's just plug and chug, right? This is something we could do a little bit more with. So this is fine. Why don't you go ahead and go back and try number 32, and I'll come back and we can compare answers. Okay, so I see that a sub 3 equals negative 75. I see that a sub 6 equals negative negative 9,375. So negative 75 equals a times r to the n minus 1, and n is 3, so that's 2. And negative 9,375 equals a sub 1 times r to the 5, right, to the 5th power. So this is a little different, but not much. Can't we just divide both sides by r squared? Then come over here and say this number equals negative 75 over r squared times r to the 5th. And then, oh, just a minute here, let me delete this. So then we've got, what do we have? We have negative 9,375 equals negative 75 times r cubed, right? Because we're going to subtract those exponents. And that number divided by that number is 125. I did this earlier. Didn't know that off the top of my head. Cube root of 125 is 5. And since I know r is 5, negative 75 over 25, because it's r squared, is what the first term is. So that's the negative 3. So negative 3 times 5 to the n minus 1. And we've got that term. Okay, so that's okay. Okay, so now we're into arithmetic or geometric series. So we're adding up the terms of a geometric sequence. And it's a little bit different formula. And here's the formula from the front page. And this is a partial sum because we're only adding up some of the terms. And so what's a little tricky about some of these is, well, let's do 15, and then maybe we'll come back and do 13 later. I see that this is an explicit formula for geometric sequence. I see the first term is 42. Of course, I saw that. I see the common ratio is 1/6, and it's raised to the 8th. But remember, that's n minus 1. So aren't there going to be 9 terms? So I know a sub 1 equals 42. I know r equals 1/6, and I know there's 9 terms, and that's all I need for this formula. So 42 times 1 minus 1/6 raised to the 9th power over 1 minus 1/6. So let's see what we get here. So that's going to be 42 times 1 minus 1/6 to the 9th power, which is going to be some huge number. Now, my graphing calculator might allow me to do this. Let's see. Raised to the 9th. Math, fraction. Nope, it's not. It's not letting me do that. What if I do it this way? 1 minus. Clear. Well, what's 6 to the 9th power? Let's do it that way. So that's going to be, like I said, some huge number. So that's going to be 1 minus 1 over 100,77696. Huge number. All over 5/6, right? So here's the shortcut. What I would do is I would take a calculator. We could certainly do this out algebraically, but that's an awful number to have to deal with. All right, so what I'm going to do is I'm going to get the decimal version of this. I'm not going to round it all. Whoops. I'm not going to round it all. In fact, I could do this thing on top. I could go 4 times parentheses 1 minus 1/9 to the 6th, or 1/6 to the 9th. Close it. It'd calculate some decimal number, and then I'm going to times that by 6 divided by 5, or I divide the whole mess by 5/6. Okay, and then that will be probably a decent number. Well, let's see what it is. It's going to be. I wish I was doing this in class under the Elmo for you, but I'm not. So I'm going to do 1 minus parentheses 1 divided by 6. Close the parentheses. Raise that to the 9th power. I'm getting 0.9999999, a whole bunch of them, times 42. And now I can either divide it by 5/6, or I can times it by 6 and divide it by 5. And then I'm getting a decimal. The decimal I'm getting is 50.3999995. I'm going to see if my calculator will convert that to a fraction. And it doesn't. So I guess that's the best we can do without getting fancy with the issues. But you see how that wasn't too bad? I mean, we were able to find the number of terms. We were able to find that we knew the first term pretty easy. But that's all it is. Now, number 13 is a little bit different from that. Here, let me delete some of this. What they aren't telling me, do you see the difference here? Is I can find the common ratio easy enough. Isn't R equal to 2? Because it's just 6 divided by 3 or 12 divided by 6, blah, 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 blah. But they aren't, and I know the first term is 3. But they aren't telling me how many terms. But I can create an explicit formula. I can create an explicit formula where it's going to be 3 times 2 raised to some unknown n minus 1 has to equal 12,288. And then we can just solve this equation. Oh, we'll divide by 3, right? So 2 to the n minus 1 equals what's 12,888 divided by 3. So 4096. Now I know that's 2 to a power, but I don't know 2 to what power. So I'm going to solve this exponential equation by rewriting it as a logarithm. Log base 2 of 4096 equals n minus 1. And then I'm just going to apply change of base, right? Log of 4096 divided by log 2. So log of that answer divided by the log of 2. I'm getting 12. That's equal to n minus 1. So I'll add 1, so n is 13. So n equals 13. So all that work just to find out how many terms there are. I mean, I guess I could have counted how many times I had to multiply 12 by, 12 times 2, count it. But what if you messed up? This is a pretty surefire way, and that's not hard. So So let me see if I can't do some deleting. Oh, I don't want to delete this. Let me see. Can I move it over? Oh, here we go. So now we'll just apply that formula. 3 times 1 minus 2 to the 13th all over 1 minus 2. So again, I'm just going to grab my calculator. 1 minus 2 raised to the 13th. I'm getting negative 8191, and that's over negative 1, so I know the negatives are going to cancel out. So all I got to do is multiply that 8191 times 3, and there's my answer, 24,573. So the first 13 terms of that sequence adds up to a little over 24,000. We're pretty close to 25,000. Okay, so that's a partial sum. Oops, I got to stop this. Okay, so now the very last thing I'm going to do in this video is how do you find the sum of an infinite geometric series? So what did you do? Well, the formula's on the front page. So there's a couple of things that's going to happen here. Well, if I have, let's say I have an arithmetic series, or an arithmetic series. I don't know, let's make this up. But if I start with 3, I'm going to add 2. The common difference is 2. Plus 7 plus 9 plus blah, 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 blah. What's the problem with this? Well, aren't those numbers getting bigger and bigger and bigger in each time? So I'm going to keep adding on a bigger number. So what's going to happen, I'm always adding on a bigger number. It's never going to settle down to a single number. So it doesn't converge. In other words, the terms in the sequence don't converge to a single number. So we can't find the sum of an infinite arithmetic sequence or series. Okay, and the same thing with the geometric series. What has to happen is we can't be. Let's see here. Well, let's look at. Let me come up and look for these. Okay, number 26. Do you see how those numbers are getting bigger and bigger? No, they aren't. They're getting smaller. No, just a minute here. Let's come up here and look at one of these geometric series. So do you see this one here? That is always getting bigger. Each term is getting bigger and bigger and bigger because we're always doubling it by 2. So this will not converge. And the reason I know it won't converge is because R is 2. In order for it to converge, R has to be, well, technically it has to be less than -1. It has to be bigger than -1, and it has to be less than +1. The negative, when the common ratio is a negative number, it's kind of weird, but it does converge. It does settle down because it's always that smaller negative number or positive number, and eventually it'll settle down. It'll go to 0, right? Not they'll always go to 0, but they'll be smaller and smaller. Will they go to 0? Oh, I said that. Well, eventually we got to add in basically 0. So I guess that is true. That the last term, the infinite last term, will be 0, or getting towards 0. So what you got to do to ask yourself, will this infinite geometric series converge? Well, R has to be less than 1, or more than -1. All these examples, R is positive. So let's delete this here. And so let's do number 25. So I see number 25. 3 over 6 is 1/2. 3 over 2 divided by 3. Well, isn't that divided by 3 over 1? So 3 over 2 divided by 3 over 1. I hope you're realizing where this is going. It's times 1 over 3. The 3's cancel. R is 1/2. So yeah, that's going to converge because the ratio is less than 1. The common ratio is less than 1. So the formula for this, and you can see this on the front page on this handout, it's a sub 1. You take the first term divided by 1 minus R. So what do all these terms equal? Well, it'll be 6 over 1 minus 1/2. Well, 6 over 1/2 6 divided by 1/2, I hope you're seeing that this is 12. 6 over 1 times 2 over 1. If I add this out, if I find 100 terms and add them up manually, it'll be getting closer and closer to 12. If I do 1,000 terms and add them up manually, I'll get 12. So that's how these infinite geometric series work, okay? And I don't know if I need to do another example for this. You'll want to watch, there's one on the Micro Math assignment, they're asking you to find an X, and it's a little bit tricky. You'll want to do that. And then there's one about a bouncing ball. You'll probably want to watch that video too. But that's what an infinite geometric series with. This video is getting long enough. Should be set to start the Micro Math assignment though. Great, whoops.